sure what happened, but seems to be working now. Okay. Sorry for the delay. Hello. Okay. Yeah. So let's start. So quick review from last time. So last time we talked about a lot of group theory. We go through this multiplication group of PQ, and we prove that. So we talk about a lot of group theory, but remember thing to actually there are only two things we need to use. So first thing we use is this result that if you think about this multiplication group of n equal to PQ, so we should actually give it a name. So let's call it like G sub n. Okay. So if we call this multiplication group of mod n equal to PQ, so let's call this G or G sub n. Then we prove that the psi of n, which is the number of things in G sub n, is P minus 1 times Q minus 1. Because all the elements can be put in this table 1 to 1. This table of what happened if you mark P and what you haven't mark Q. Okay. And this is 1 to 1 to all the elements in is G sub n. And then the other thing we need to know about group theory is that the order of a subgroup will divide the order of the whole group. So then we think about this multiplication group of G sub n. Then we find out that if we consider this subgroup generated by your ISA message m squared and cube all the way to the n minus 1, then this is a subgroup in this G sub n group, and so the number of things in this subgroup, which is obviously R, should divide the order of a group, which is psi of R. And this is one of the crucial steps to prove that your RSA decoding actually works. So our RSA decoding key is this D, such that E times D is some constant times 5 plus 1. And then so you get this M to the C. Yeah. So we know this M to the ED is about M times something that's something times phi n, and M times something that's constant multiple of phi n, and we know constant multiple of phi n is another constant multiple of R, and M to the R is equal to 1 mod n, so this thing is just 1 mod n. Okay? So that's the basic of RSA decryption, and there are some examples that are walking through everything, and here is an example of tells you that how do you find the decryption key by running the Euclid's algorithm backward, and here is another example of decryption for RSA. Okay. So that's some digression to classical computing about how RSA works, and a little bit of group theory if you haven't seen about it. It's quite useful in all kinds of cryptography. But anyway, so now we are going to go to a totally different topic, our Grover's algorithm. So this is our second useful quantum algorithm. So there are two important class of quantum algorithm, that's Shor's algorithm and the Grover's algorithm, and we already seen Shor's algorithm. Now we are going to talk about Grover's algorithm. And Grover's algorithm, well, it's quite different flavor from Shor's algorithm. So it solves a very general problem. So Shor's algorithm can be generalized by basically solving factoring and mathematical problems that have similar structure. But Grover's algorithm solves this search problem. So this search problem is search problem is a problem such that you have big N items, and you want to find one or more marked item inside out of them. So something like if you want to brute force the NP problem, right? Then you can like search through all the possible witnesses and see any of them will will satisfy your NP maybe clauses or something. Okay. So it's a search problem. It's a very general thing you will do in your algorithm. Maybe you want to try passwords to something, and that's a search algorithm. Or sometimes maybe you say you want to invert the one-way function. You can also try all the possible input. Okay, so f of x equal to y. Okay, so that's search. And well, so classically, if you want to do brute force search, and you want to search big N item, then you probably need order big N time. But Grover's algorithm, it only need order square root N time if you can do things in quantum superposition. So you see there is this square root N versus big N difference. Okay, and the classical there is also so there is upper bound and lower bound. So classically it's also actually theta n. But quantumly you can do order square root N, and there is a maximum lower bound such that saying that you also need omega square root N. So it's actually theta square root N. And so you see here that the speed up here is smaller than Shor's algorithm, right? Shor's algorithm, we keep saying that it's exponential speed up because, yeah, because it's like square root L over, sorry, in terms of the number we have, the Shor's algorithm keeps saying like L cube vs I think is 2 to L, and then maybe taking a square root. But anyway, that's an exponential difference. But here, this is a polynomial difference. It's n versus square root n. So it's a smaller speed up. Nevertheless, it's also very useful because how common search it is. How common search is in designing any algorithm. You can think about a lot of algorithms you do are basically just doing brute force search. Maybe like sometimes you search through a decision tree, like breadth search or depth first search, etc. Okay. So it's very useful, and you can build a lot of quantum speedup from this. Also, the theory is very complete or very robust because we have a matching lower bound. So in Grover's algorithm, we have no lower bound, but in Shor's algorithm, we didn't really have a lower bound. But for Grover algorithm, we have this very tight theoretical lower bound. And we're going to see that because we can analyze it very nicely through quantum query complexity. Okay? And yeah, we can analyze this through quantum query complexity, and its quantum query complexity actually equal to its quantum time complexity. I guess that's also true for Shor's algorithm, but things are a lot more complicated. We skip over the Oracle version of Shor's algorithm, but you can look it up on the textbook. It's also quite nice. It's basically the same thing, just that when you do, so Shor's algorithm has like HEDMA, and you do this control thing, right? Control U to a T and QFT minus 1, the period defining part. So if you want to do the Oracle version, then you say this U to a T is given by Oracle. But then you find out the Oracle complexity is quite a lot, so it's very complicated. But anyway, we are in Grover's algorithm, so let's erase this. Okay, And so let's start with a review about query complexity because we are going to talk everything in quantum oracles. Okay. So quantum oracles. Now we actually change the notation a little bit. So now we call our oracle. So oracle, remember, it's like a black box. It represents some kind of subalgorithm. So for example, in this example, the oracle might be representing trying out your one-way function or trying out your verification circuit for your NP-complete problem, etc. But anyway, so we abstract it into some kind of black box. So just some blocks you can put in your circuit. And we call that OF tilde. Okay, so F is a function. And so we change the name a little bit. So previously we called this in UF, but now we call it OF because it's for Oracle. And we give it tilde for reason you will see soon. Okay. Okay. So the quantum oracle we call it OF tilde. No, it's just a name. And what I actually do is this. So of tilde, there is an input register and a record register. This is something like the two register. And what I do is you want to compute f of x here. Okay? So you will look at the input register and don't really change it. And you will compute f of x and add it on the record register. And okay. So then you have this O plus here, which is a little ill-defined if your OF is many bits, but we only have 1 bit. We're going to restrict to 1 bit, just next line, so doesn't matter. Okay. So anyway, we need this to be O plus because remember, OF tilde is a quantum gate, it's a unitary, so it needs to be reversible. So here the things should be reversible. Everything should be 1-to-1. Yeah. Okay, so that's OF tilde, and as we said, we are going to restrict to these two binary functions to make things a lot easier. Also, for such problem, we only need a binary function. Okay. So the input is not quite binary. We just discretize it. So input we can encode it whatever. As long as we have discrete input, we can describe the input in bit string. So it's like n bit, small n bit string. And so this is really binary. So now we restrict output to binary. Output now we say we just look at output as either 0 or 1. Okay. And this is, so we have seen this quite a bit. Remember so binary function Oracle we're doing like Dioch-Josa algorithm or Brazilian-Varanic algorithm. And there's also seen in Simon's algorithm or Shor's algorithm that the Oracle are not necessarily binary. But for search, being restricted to binary is perfectly fine because basically the only meaningful information you get over your Oracle is whether you hit the mark item or not. So you can just say you hit the mark item, then the result is 1. You don't hit the mark item, result is 0. Okay? So we just restrict our function, the function related to Oracle, this binary function 0 or 1. Okay. And now once again there is this very confusing thing about big N and small n. Okay. So why is it confusing? Because now I want to talk about input size. Okay. So the input size, small n or big N, then that depends on what are you inputting. Okay. So as we say, f is a function. Obviously, there is a function. There is an input to this function small f. Then that is small n bit string. You can put it into f, and it will tell you 0 or 1. But then there is but the f itself, in another sense, is the input to our function of finding the mark item inside f. Okay. So yeah, so we will kind of being a little ambiguous about what is input in our problem, but mostly we think f itself. So everything about f is input to our problem. So input size is actually this big and big string, and that's just as we write here. It's the truth table of small f. Okay, so yeah, let me try to So right, so small f has small and big string as input, and so there are 2 to the n possible input to small f, and each of the input can have output 0 or 1. So the total possible form of f, or the total possible number of truth table, is 2 to the big N. Okay, because f of 0 can be 0 or 1, f of 1 can be 0 or 1, f of 2 it can be 0 or 1, etc. So the truth table of f is this big N big string. Okay. And yeah, as we said, big N big string. So the truth table is a big N big string, and this is we think about as the input to our problem. So our input is this function f, its whole truth table, and we are going to query this whole truth table in quantum superposition, because we have a quantum computer. We can compute every value in superposition. Okay. Any question? No? Okay. Let's keep our review. And yeah, just as we said, we only care about this being 0 and 1 because now we are thinking about such problem. And then we just say f of x equal to 1 when it is like a mark item, which is something we want. So maybe when you invert your h function, so your one-way function, when you hit your f of x equal y, then we say that f of x equal y, etc. Okay. And obviously the other way around, then f of x equal to 0, that means we didn't hit it. Okay. So it's 0 and 1 in all the blocks. And in our search problem, we want to find x, or one of those blocks, or some location, such that f of x equal to 1. This is an abstraction over all kinds of search problem. Okay, and then we further restrict our cost of our algorithm to this quantum query complexity. So we abstract over the subalgorithm to this oracle f, and we further restrict our attention of our algorithm design into this quantum query complexity. That is, how many of those OF, okay, so this OF, we actually put in our algorithm. And so we think this is kind of a costly step that require quite a bit of computation, and we just want to minimize the number of use of this. And sometimes this is justified, sometimes it's not. But I guess most of the time it's justified. And it's very justified in Grover's algorithm, because you are going to see that every other number of other operations in our Grover's algorithm is same order as the number of oracle we put in our Grover's algorithm. But anyway, back to a very abstract level, quantum query complexity is number of OF you need to put in your quantum circuit to solve your problem. Okay. And we have this mental picture we had before. So your algorithm in a very general form will initialize with a whole bunch of 0 in all qubit. Then we will do some kind of unitary that doesn't call your OF, and then we'll do our OF, actually OF tilde here. Then we can do another unitary, then another OF tilde, etc. and finally a unitary, and we do measurement and we get the result. And also there are some maybe not quite in C but those unitary make more qubits than your oracles. Okay. Yeah. And anyway, so the query complexity is just the number of layers that contain the oracle here. So yeah. So the query complexity is just how many of those oracles calls we have in our algorithm. And we don't care about how complicated all those U are. They can be anything. If we are thinking about query complexity, then we only care about minimizing the number of oracle calls. Once again, it's very theoretical. Sometimes it's not very practical, but it's a cool thing to think about, and also it gives you a way to provide precise lower bound. Okay, and we are a bit slow. Okay, maybe we will not be able to.
Query all of the oracles is complexity is
what?
Square root bigger.
No, so big O square root means that if you want to do the search problem, which is finding a 1 in oracle, then you only need all the square root number of layers in your algorithm to solve the search problem. Okay. And yeah, but okay, so here now this big N is the same as this big N. Yeah. So now, so if your oracle is like this, has big N values in your truth table, then then also only require square root big N number of calls of it to do this go over search problem. Okay, and I guess let's keep the review. We might not be able to touch too much about the go over algorithm, but more review. Now we are going to get rid of this tilde by doing something that hopefully you are familiar with. Still remember that is phase kickback. Okay. So this HR register of OF is kind of annoying. So we're going to change it into the phase version of the oracle. Okay. Let's skip a little bit. So phase version of oracle is this. So you want to apply OF on x, then you only get a -1 to the f of x times x. Now this is totally quantum because classically there is no idea, no concept of being this phase. Okay. And here is a small reminder of how you do the phase kickback. So if you put a second register as the minus state, and you apply OF on it, then when OF equals 0, obviously nothing happens, you still get the same state. And OF equal to 1, then you will, what am I saying? If f of x is equal to 0, then nothing happens. Then f of x equal to 1, then you need to add 1 on those two things. Then 0 becomes 1, 1 becomes 0. You swap those two, but you see there is a minus sign, so you get the h1 minus sign. And yeah, so when f of x equal to 1, you get the h1 minus 1 sign. So you get this -1 to the f of x phase. And then you see that this minus thing always stay minus, so you might as well discard it. It's just an h1 theta thing. Then you can really get that. Yeah, so if you just pretend this minus thing doesn't exist, then you get an oracle such that you apply OF to x, you get -1 to the f of x, and the sense x. And because we are going to keep using this oracle, so we put tilde on the original oracle and no tilde here. Just make our notation easier. Okay. Okay. And so this we should have seen many times. So we have seen this technique in Dior-Josa algorithm. And also you have already proved it. You should have already proved this in your homework. So if you don't remember, you should go back to see homework 7 a solution where we prove that if we have what is that? Okay, so so we prove that this OF tilde, this standard basis oracle, is equivalent to this phase version of oracle but with HR control. So you have shown that there is a one-to-one correspondence by doing some HEDMA. Okay? And the control version of oracle is very similar. It's -1 to the f of x, but also times y. So this oracle is controlled by the second register y. If y equal to 0, then nothing happens, and y equal to 1, you get this control version. Okay. And now something about this. So obviously this thing is more powerful than this thing, okay? Because you get this extra control. And something little to say about this is that this is more powerful and it's necessary if you want to go back from OF to OF tilde. Okay. So you need to have controlled OF so you can control OF tilde from control OF, but actually not possible to construct OF from just to construct OF tilde from just this OF, because anyone want to answer? What information are you losing if you only have OF? And the answer is that OF, you are losing a global phase. So remember, global phase is not something you can see, right? So if you have f is O0 function, right? So your f is O0 function, then OF of x will equal to x always, right? Because nothing. But the f is O1 function, then OF of x equal to what? Want to answer? Okay. Anyway, O of x equal to -x, right? Because they always give you a -1. Okay. But those things are actually the same thing because they are different by a global phase. This 1 here and the -1 here is a global phase. You cannot distinguish them. Okay? So actually, if you only have OF, you cannot distinguish O0 function and O1 function. And obviously that's a trouble, because if you look at OF tilde, it's very easy to distinguish those two. Okay? But if you have a control version, then you can distinguish them. Okay? So that's why you need a control version of the oracle. And now we're about 15 minutes to actually talk about the Glover's algorithm. I think we can go over a very high level idea and leave out some details. And let's see, 15 minutes. Anyway, so let's just look at the algorithm here. So the algorithm is very simple. As we say, we'll start with O0 state and raise H3, no HR, and see nothing. You are just going to use small n bit. So 2 to the small n equal to big N, something like this. And things are all starting with 0. And you apply HEDMA on every qubit. So this is something we've seen a lot of time. You will have the summation of everything here. Summation, let's say like k from 0 to a -1k here. Okay, so you create equal superposition of everything, and we actually will call this equal superposition of everything just phi. Okay, because we're going to say a lot about it. And then we'll keep repeating this so-called Glover iteration thing. Big O order square root n 10, then we just measure. Okay. So it's very simple. And So non-quadrant is what's this big G thing. Okay, so it's something in those 4 steps, but actually more like 2 steps. So the first step is apply our OF. So remember OF is OF of x equal to -1 to the f of x. Okay, so this is the only place you need to use the oracle. You apply the oracle as you might expect it. And then there are 3 steps, or this hand to the n, and some -1 thing, and some hand to the n thing. And maybe let's do a spoiler because we are short on time. So those 3 things together is a very complicated way to say we are doing a reflection around psi. So it's 2 psi minus identity. Okay. So remember, psi is this totally mixed state. Not totally mixed state, sorry. Psi is this equal superposition of all state. Do we have it written somewhere? Okay, it's here. Okay. Psi is this thing. Okay. So Grover algorithm basically just repeats this G thing. G is called Grover iteration or Grover operator, and OF is our oracle. Okay. So I guess some analysis here, obviously you see that every G contains 1 cause to your oracle. So the number of G, and this obviously H hat doesn't contain any cause to your oracle. So the number of G is the number of calls to your oracle. Okay, it's 1 to 1. And some notation thing we need to set up straight. So it's a bit confusing because OF is called oracle, and G is usually called Grover iteration or Grover operator. So Grover operator I think is okay, but a very confusing notation sometimes people will say is Grover oracle. Okay, so when you say Grover oracle, now it's a little confusing. Are you saying G or OF? I think most of the time when people say Grover oracle, it means OF. But for safety, you better not say this. Okay, so let's keep our notation straight, where OF is oracle and G is Grover iteration. Okay. Anyway, so that's notation thing, and let's try get a 5-minute idea of why this algorithm works. Okay, so as we said, there are 2 things we do here. So one thing is obviously our Grover. Sorry, now I'm going to say that. One thing is obviously our oracle here. So oracle is -1 to f of xx. And the other thing, we call this reflection around totally mixed state phi. Reflection. Okay. So this is reflection around phi. Why do we call it reflection around phi? Because if we go to this nice 2-dimensional space, right? So we can think about 2-dimensional space spanned by 2 things. So one thing is this, not actually phi, it's actually psi. So this psi is the equal superposition of every state. And we can think about another state that's the equal superposition of every mark item. So for now, you can think maybe there is only 1 mark item. So then it's just a mark item state. But we are having more general thing here. So assuming we have n mark item, and we can think about this equal superposition of all mark item. Obviously, it should be normalized by the square root of m, right? Okay. And if we think about the space, this 2-dimensional space spanned by those 2 states, obviously there should be these two should be, most of the time, they should be not the same. If they are the same, it's very easy to find a mark item. But if they are not the same, then you have two vectors, you can span a two-dimensional space, right? Two vectors, then you do whatever thing, and you see that they span two-dimensional space. And but they are not orthogonal. And so what is actually orthogonal to alpha, to beta, in this two-dimensional space is also something very nice. It's just the equal superposition of everything that's not marked. Okay? That should make a lot of sense, hopefully. Anyway, so that's that. And now we think about what our Grover iteration do in this subspace. Okay? So we will start our algorithm with being this state, because that's what we do. We start with O0 when we do head mod, and we start with being this state, right? Equals superposition of everything. And then the first thing we do is we will apply the oracle. And what the oracle do? Okay. Oracle does OF of x equal to -1 to the f of x. So if f of x equal to 1, then you get a minus sign. And if f of x is not equal to 0, then nothing change. So but we know alpha are all the things that with f of x equal to 0, and beta are all the things that with f of x equal to 1. So beta, after getting applied OF, will become minus beta, and alpha will stay in alpha. And if you look at this two-dimensional space, it means that wherever you have a state here, then you think about it as alpha and the beta component. And the beta component get a negative sign, alpha component stay the same. So what happens is you are going to reflect around alpha. You get to this state. Okay? So this is one reflection. So you see that in the two-dimensional space, your oracle OF is this reflection around alpha. And what about this 2, 5, 5 minus I? Well, it's basically the same thing, right? So you see that you can decompose everything into this space, this basis of phi, and since orthogonal to phi, let's call this phi perpendicular, right? So and so you do the 2, 5, 5 minus identity, and if you put phi here, then you find out that you have 2 phi minus phi is still phi. So the phi component will stay the same. And the phi perpendicular component is perpendicular to phi. Then it just get, so you have phi perpendicular here. Then phi perpendicular and the phi are obviously orthogonal to each other. So you multiply this on this, then you got 0 here. So you just get only left, everything left is minus identity times phi perpendicular, so it's minus phi perpendicular. So whatever you have a thing somewhere, and you see the perpendicular component get a negative sign to here. So what this whole thing do is it's going to reflect around your phi. Okay? And okay, well, exactly on time. Okay. So what happens if you do two reflection on a plane is that you will get one rotation. And do we have a better picture? Not quite. Anyway, so we have a very geometric representation here. Wait, do we actually have? No? Okay. Anyway. Okay, so maybe I can just draw it here. So what happened is we have these two axes of rotation. So this is alpha. Remember, OF is reflection around alpha, and the 255 minus I is a reflection around this psi, sorry, 2 psi psi minus I. Okay. So if you have say something here, then you do a reflection around here, or here. Oh, we have enough time, right? So let's do the algebra. So this angle, for reasons, we'll call it theta over 2. And let's say this angle equal to alpha. So let's do geometry. So we start with here. Then we do a reflection down here. Then this angle is obviously, okay, that's not as close. Is obviously alpha plus theta over 2, right? Just this angle should equal to this angle. Okay? And then we reflect around here. And so, anyone want to answer? No, the angle. So what is the angle here? Okay. So this angle should equal to this angle, right? And this one is alpha theta over 2 plus theta over 2. So this whole angle is alpha plus theta. Okay? So this is elementary school math. And so what's important here? What's important here is, well, what we really want to know is this angle. So it's alpha plus theta, subtract the alpha you have with. So this is theta. Okay? Okay. So what we prove is that when you do this Gover iteration of two reflection, what you actually do is you rotate your vector by theta. Okay? And we're going to see that the theta over 2. So theta is about 1 over square root n, or more like n over square root n. But okay, so if we think n equal to 1, then that's about 1 over square root n. And so you need to do about square root n rotation to rotate your starting state to here. Okay. So that's why you do Gover algorithm. Okay. So n is bigger, then this theta gets smaller, then you need to do more rotation to really stay up here. And once you rotate your state up here, you just do computational measurement, you will get something beta, which is a Mach item. Okay. Okay, so we are about on time. Any question?
I'm sorry, what's the Mach item?
Oh, Mach item is f of x equal to 1. So this is the thing we keep talking about. And I guess we didn't quite say, but is f of x equal to 1. So we want to find some x such that f of x equal to 1. Okay? Okay. Okay. So next time we'll do this a bit more carefully. Again. And hopefully we don't have trouble with OBS anymore.